Today is the 25th. Ooh, 425. Nice. And we're just doing more logs. So this is the part of the lesson that I opted to leave out. So ideally, you're getting close to done with that first assignment. Because then today I'm going to add on. So Delta Math offers level 1, level 2, and level 3. I've already given you an assignment on levels 1 and 2. Today you'll learn how to do the problems in level 3. And then this will be a separate Delta math assignment. So it'll be assignment number 52. It'll assign itself here in about 10 or 15 minutes. So about the time we're done with these notes, I only have 6 examples today, so it shouldn't be a problem. And then you can work today. For you guys who are gone, you can spend today doing your test corrections and then do your homework on your own time, like over the weekend. And those of you guys that were here, you can just work on your Delta Math. So there you go. So yeah, these are a little bit trickier. There's a different method for this. So I'm just going to get right to it and show you what the problems are going to look like. Thank you. I mean, if you have a wicked, nasty, good, deep understanding of logarithms, you could actually reason your way through the answer to this problem. Like you could figure out why the answer is 3/2. But that's a lot to ask, like when we just started logs like 3 or 4 days ago. So there's a method to this. This works every single time. And the trick to this, when you see this issue, like right away, you should see the problem because I'm asking you to take 25 and raise it to some power that would equal 125. And that's just not normal. Like we're used to saying, something simple like, log base 4 of 64. Well, that's easy. That's just 3. When it's just directly evaluatable, we don't need a larger weapon for that fight. But these ones are a little bit more complex because 25 cannot raise to any whole number power that's going to turn it into 125, right? Like 25 to the first is 1, 25 to the second is 625. And so you're like, wow, how am I supposed to make 125? Well, you do it like this. And this one trick will get you through. This is it. This entire assignment number 52, you can do every single problem like this. And here it goes. All you're simply going to do is on the right-hand side of this, you're going to set it equal to X. Because at the end of the day, that's really what we've been doing the whole time anyways, is just like solving for X that wasn't really there. But physically having an X here is what's going to make the difference because it's going to enable us to write an equation. And then the equation will be pretty simple, I think, for you to solve. The trick, though, is once you identify one of these situations where the base and the argument don't play nice together, then just put X and water cycle it out. And so I'm going to take the 25 and I'm going to raise it to the power of X, and I'm going to set it equal to 125. That goes all the way back to Monday or Tuesday when we first talked about logs. That's that always there relationship between the base, the logarithm, and the argument. And so if I write that water cycle out, it converts into what we call an exponential equation, and it says 25 to the power of X must equal 125. That's nothing we didn't already know. Like we understood the mission, but to see it as an algebra equation like this is going to enable us now to do a fancy little trick. So the trick is to solve an equation like this is to make these numbers at the bottom the same. And what I mean by that is they're both powers of the same number. They're both powers of 5, right? And so I can take the 25 and I can rewrite it as 5 squared. And then I raise that to the power of X. And then on the right-hand side, I can take the 125 and I can write it as a power of 5. What is 125? How many 5s does it take? 5 to the third power. Yeah, so this is 5 to the third power. And in math, it's almost just common sense, but it does bear saying out loud that if you have an equation, let me just give you an example. Like if I said a to the power of X is equal to a to the power of Y. It 100% has to be true that x has to equal y. There's no way you could make sense of that if those exponents weren't identical. And so we're going to apply that logic to the situation on the left. So the exponent on the left is 2 times x, which we know as 2x. And the exponent on the right is 3. And as I just said over here in this sort of weird looking example, then those have to be equal to each other. If two bases to different looking powers equal the same thing, those different looking powers, they have to match. And then what pops out is a little sixth grade equation. Like it's no longer an 11th grade math problem. It's now just, are you kidding me? Divide both sides by 2. And you figure out that your logarithm the whole while was x equals 3 over 2, like that. That's our go-to trick for harder logs. You could do that every time if you want, by the way, but it's just like, why bring a gun to a knife fight, right? But this is a gunfight. Like these problems are harder to evaluate using just reasoning. So we concretely stick in an x, write an equation, and solve it. So I hope that made a little bit of sense, but there's 5 more. So hopefully your understanding will get progressively better over the next 5 minutes. So let's do log base 64 of 16. And again, that's a very complex looking question. That's me asking you 64 raised to what power equals 16. So again, the trick is let's just make it official and slap an equals x over here on the right-hand side. And then we're going to water cycle it out. And by doing that, what we do is we convert it from what we call a logarithmic equation into an exponential equation. So we're going to say 64 to the power of x equals 16. And when you write that equation out, it looks like this. And the idea now is just to play the matching game. And that is to say, I need to turn 64 and 16 into powers of the same thing. And there's a couple ways you can do this, but you always want to pick the biggest. This 64 and 16 are pretty unique numbers because like 64 can be written as 2 to the 6th power and 16 can be written as 2 to the 4th power. But they can also use powers of 4, right? And so 4 is the bigger base is always going to save you a little bit of reducing at the end. They'll both work just fine. But I would choose to consider that 64 is 4 to the 3rd and that 16 is 4 to the 2nd. Bigger base equals smaller exponents equals no reducing or less reducing at the end. So I'm going to take the 64 and I'm going to rewrite it as 4 to the 3rd. And then I'm going to raise that to the power of x because that's just still there. And then 16, I'm going to rewrite as 4 to the 2nd. And then I'm just going to play the matching game. And I'm going to say, well, I don't know who you are, 3x, but I do know that you've got to equal 2, right? And if 3x equals 2, what does x equal? There you go. So the missing logarithm there is 2/3. And that works every time. So obviously there's going to be some fractions in the mix. So let's talk about a fraction and how to do that. You'll find that it's the same process. It's just a little bit more difficult for some people because fractions can be a little bit off-putting for some of us. So let's do log base 16 of 1 over 1024. So what you want to do here is, again, look for a common ground. First start by slapping the x over here and then cycle it out. I can keep drawing that little cycle every time, but eventually you don't need it. Like you understand that it's this to the this equals this. So the equation in its sort of raw form says that 16 to some power is equal to 1 over 1024. And the thing about 1024 is he's not directly a whole number power of 16. But what is the common base that I could turn them both into? It is 4 again. So like I can take this circled yellow number and write it as 4 squared and then raise that to the power of x because that was already there, right? And then put my equal sign. And you should know this, having been working with logs for the last couple of days, that what is that? 4 to the what power makes that? 4 to the 4th, that's not gonna Yeah, but we want to not do this. And this is a pretty common error is people would do this. And just understand that 4 to the fifth equals 1024. And that, yes, that does not say 1024. So good job, Kyla. We need to use a negative exponent in this case. Because remember, it's the negative exponents that cause things to go flippy. Okay. But again, we've accomplished our task. We've set this thing up so that the numbers on the bottom are the same. 4 is equal to 4. And from this point on, the fact of the matter, 1,000,000% is that that exponent and that exponent have no choice but to be identical. They must be equal. And as always, what pops out is a real simple equation. Divide by 2 and x equals -5/2. Done. Feeling good? Right. So these last three should feel not so much like we're learning it anymore, but let's just lock in and make sure that we're solid. So let's do log base 27 of 243. So putting the x over here enables us to structurally see or create an equation. So what's the equation going to say right now? 27 to the x, just like that. And now it's a hunt. And that's where your table comes in handy is for you. You probably already knew this one, quite frankly, but what is a base that can be created? Yeah, 3 can be turned into both of those, like using exponents. So this yellow number becomes 3 to the third. And then again, we just insert the x. And then this yellow number is 3 to the what? To the fifth. And then inescapably, logic kicks in and we say 3x and 5. I need you guys to equal each other. And then that's the beauty of algebra is you just are always forcing something to happen. So what algebra eventually becomes is not a class so much as just a set of tools. Like I want something to happen, make it happen. Divide both sides by 3 and x equals 5/3. Right. All right, I got 2 more on my note card. They're both fractions, so let's knock these out. Let's do log base 256 of 1/32. Go ahead and add the obligatory x. And we're off. Initially, the equation says 256 to the power of x equals 1/32. And 2 is our guy here, right? And that's, again, use your sheet. That's what it's there for. And you'll find that 256 and 32 can commonly both be created as powers of 2. So what is 256 as a power of 2? 2 to the 8th. And then reinsert the x that was already there. And what is 1/32 as a power of 2? 2 to the negative. -5. Very good. Caught the negative that time. And then you set the equation or the exponents equal to each other. The bases literally just become redundant. They just cancel out. And so 8x must equal -5. What does x equal? Negative. Good job. You could give me a week to try, and I couldn't think of a better way to teach you how to do that than exactly the way we're doing it. So this is a pretty smooth method. And like I said, you don't need it all the time because some problems you can just do through what we call inspection. Like you just look at it and look, you know what the answer is. But these are tougher. So log base 49 of 1/343. Start by slapping an x on there and then construct your equation. So we have 49 to the power of x equals 1/343. And what are those both powers of? Yeah, they're both on your 7 list. And so we're going to take the 49 and rewrite it as 7 to the power of 2. And then raise that up to the x. And then we're going to take 1/343. What is that? 7 to the negative. 7 to the -3rd. By this point in the lesson, you're probably just on autopilot, right? Like you get it. You know where we're going. Stick the x, make the equation, make the basis the same. Boom. And so if 2x is forced to be equal to -3, what does x equal? -3/2. That's all there is to it. Okay. So all what we just did, those 6 examples are going to just carry you completely through assignment number 52. So the goal for today is either you're going to be working on your test corrections if you were absent yesterday, or you're going to walk out of here today with assignment number 51 and assignment number 52 both done. And if you're in the test correction category, then you'll of course need to do these over the weekend so that we can move on. Practice quiz Monday, quiz Tuesday. So got it? Any questions about that? Okie dokie. Anytime you have a log with an argument of 1, the answer is always 0. And the reason is because the only thing you can raise 8 up to as a power to get it to magically to become a 1 is 0. We know from our past at some point that anything when raised to the power of 0 will always magically equal 1. And so having said that, any log with an argument of 1, like it could say log base 47 of 1, the answer is going to be 0. It could say natural log of 1, the answer is going to be 0. Got that? So that's worth putting into your notebooks, is that if the argument is 1, the answer is 0. Take it to the bank. Got it? Okay. I will.